essence before we get started. Yeah, I'm silly.
Okay, so
Sure.
let's get started. And we're talking about the alignment potential, and we're trying to derive a mean field representation of this potential. So to do that, we just take a derivative, okay, of the potential with respect to the gradient, and we did the calculation here. And what's left is the following. So we just want to differentiate this guy with respect to q, right? Yes, and q prime again is that's an independent variable from q. So we just need to calculate this quantity.
Instead.
And the question is, what is this?
That was
Any suggestions on how we do that?
what?
Is what?
Why don't you
So we're trying to calculate the derivative of q with respect to itself, right? That's what's needed here.
That's a change in Q blade.
That is what?
The Q bar is given. Delta Q bar. There is this delta theta in terms of the maximum fluidings.
Okay, so what would that be?
Q bar is cos theta, something like that.
Okay, that's fine. So what would you say this leads to? Can you write down the result? What would that be? First, before we write down the result, what do we get a vector? Do we get a scalar? What kind of object are we getting?
This
We get a tensor, and the reason is
is a vector.
we're taking gradient of a vector, right? So it's a tensor. What kind of tensor are we going to get?
I didn't play this. I believe.
That's close to the right answer. Yes. So okay, that's good, because I guess you're thinking about the following thing, right? So if you think about, say, Cartesian space, okay, then you're saying I'm taking the gradient of x with respect to itself. So that is identity, right? Identity, that means 1, 0, 0, 0, 1, 0, things like that in 3D, okay? So we're just taking the gradient of space itself, its identity in Cartesian space. It's not the case so Q is in a unit sphere, on the unit sphere. So it's a curved surface.
Isn't it like
It is question, yeah.
is this like G? Like,
What is G?
is it related to we have this metric tensor? Is it like that?
So you would be okay. That's in the right direction. So if we do this one here, right, we get the identity in Cartesian space. If we do this on this new space, we should get the identity tensor in that space, in the unit sphere space. And how do we write down that identity tensor?
I was
Sorry. So again, I'm trying to compare these guys. So in the Cartesian space, that gradient is just a normal identity tensor, correct?
Yes.
And then I'm saying that this would be still the identity tensor, but for this curved space. Makes sense? You're taking the coordinate with the gradient of the coordinate.
That is that EX y is it the first one?
Yeah, because that's Cartesian. Cartesian identity is just the regular identity. But the identity tensor on the sphere, unit sphere, is not this guy, right? It's something else. So we can write that as I sub s. And okay, let me write this down, and I'm going to explain.
Sure.
And you can also calculate this using algebra, but I'm trying to motivate this using physics. Okay. So let's call this IS. So that's the identity on the unit sphere. So if you think about an identity tensor on the unit sphere, it has to be normal to the Q vector, right? Q is perpendicular to the surface. Therefore, the identity tensor on the unit sphere is just the regular identity tensor, but remove the part that's normal to the surface, which is QQ. So, okay, so is this, now if you do the following, if you say, if you take a dot product of Q against this identity, what do you get? Any suggestions? So I take a dot product of Q with this tensor. I can do the following, right? Dot it with I, with QQ. So what do I get for the first term here? So I'm taking a dot product of the vector with the identity matrix.
That's going to be our
Which vector?
Q vector.
Yeah, because it's identity on the right-hand side. What about here? So what is Q dot Q?
That's the magnitude.
And what is the magnitude? So then that's Q minus Q, and that's equal to 0. So this tells you that this tensor is normal to Q. Of course, because Q is normal to the surface. So this is the identity on the surface. So that's a geometric derivation. You can do that mathematically, which we're not going to do now, but we're going to do that on Saturday. Comments? Okay, that's fine. So we have this thing now, and then we can come back and assemble our derivative here, right? So we have all the pieces now together. So let's do that. So, okay, so what we have is the following then. So grad Q of U is minus 2U naught integral of P Q dot Q prime minus Q dot Q prime, then times Q dq prime. So I've substituted in this derivative in here, and I've written that out explicitly, okay? So that's what we have to integrate. Any questions? Okay, so let's carry out this algebra here. Okay. So I have two parts. We can do that separately. First one is P Q dot Q prime dq prime. The second is, so there are two things that's going on here. So I have Q prime contracted with 3 Q's, okay? 1, 2, 3. I'm running out of space here. dq prime. Okay, I've just split up these two terms into two separate integrals. Okay. So now let's look at this first integral here. What would this one be? So if you look at it, Q is not part of the integral. So we're integrating P times 2Q primes. And what kind of moment is that one? That's a nematic, right? That's a second 2Qs. That's a nematic order. Okay. So then what we have is the following. So that's Q dotted with the nematic, or QQ average. I'm going to write that as Q. So I'm just going to write out the integral explicitly here. And the second one is 3 Q's. Again, those are not part of the integral. Dotted with P, Q prime, dq prime. Okay? So I can write this in the following form. Any questions?
That's still the double dot.
Where? This guy, yeah. Double dot product, yes, correct.
She said.
And we're not done yet. So what we have discovered is the following, that the grad Q of U is this quantity here. So there's a point to this calculation, okay, which will come up in just a second. So we have this relation. And what we need is the actual rotational gradient, which is q cross with this quantity, right? So what we want is q cross this derivative u. And I'm going to skip this part. It's just taking a cross product. You can do that later on. Then what we'll have is the following. So what we get is 2u dot q cross nematic dotted with q. So the final result is actually quite simple. It's of the following structure. Okay. So what we have to do now is this is a angular velocity that the particles are going to get because they try to align, which means they rotate towards a certain direction. So we go back to our constitutive relation for the rotational flux, and we add this term there. So that's the flow part, which we had before, right? Now we add this guy here. And what else do we have? We have the rotational fusion from before. Okay? So this is the alignment term. So that is it. That's the only new thing we have in all of our equations, is now we've introduced an alignment term. Any comments on this? Okay, so then I have one question for you, which is, why is this an alignment term? Can you see that from the structure of the angular velocity? So let's think about that for a bit.
Maybe things in the electric in the system.
Sorry?
Things the electric in the system.
Why?
It's kind of the cross control.
Okay, good. You're getting to the right place and aligning with what? Which Q? There are two Qs. Big Q. That's correct. And why is that? Q is a tensor, right? The thematic. You're getting the right answer, and yeah.
If the orientation
So essentially,
is the original, then there will be no
you
collision.
see some fluctuations in the shape of the droplet.
That's correct.
And
Yes,
within the
but like
droplet,
here is a
there
tensor,
are
then, right? So we talk about
largely
orientation. What do you mean by that?
Random flow that's been generated.
Not use electric.
And if we increase activity,
Yes.
in this
Whole thing is actually correct.
what we
Like
see
here is
is
aligned with this tensor in one
this
way.
droplet is
So
spinning.
one way, because what the
as a
way to think
whole,
about that is this
and
tensor
then you generate
has
this
these
particle
principal
flow.
directions, these eigenvectors. Okay, correct? If Q is in the direction of one of the eigenvector,
That Q.
small q is in one of the direction of the eigenvector of the big Q, what happens? So Q dot this Q gives you Q, because Q is the eigenvector. Then the two Q cross product of the Q's are 0. Make sense? Okay, so it's best to write that down, okay? Suppose, you know, this is not exact math, just looking at scaling arguments, okay? Suppose E is the eigenvector, so Q would have a structure like that, right? Then I'm saying if Q is aligned with E, which means Q is essentially E, okay? Then Q dot this capital Q is E. E cross E is 0, right? Which means if you're aligned with the principal direction of capital Q, you don't get a torque. If you are not aligned, you do get a torque.
So we are trying to align.
Yes,
Aligned or not giving.
correct. And the alignment direction is just in the principal directions of Q, right? So that's why this is a nematic alignment term, because you're trying to align with this tensor, the nematic tensor. And that's exactly what we want to model. When two ellipses come together, it's a nematic alignment. Okay, so this is the physics that this term reflects. Other questions, comments?
So it turns out it's quite simple, okay, to model what seems to be a complex process. So that's the whole point of this exercise. Actually, it's not that complicated at the end. Okay, so now let's go back, revisit our equations. So this would be
What's the
equations with alignment, right? So what's changed here?
bang?
It's just in this term, okay? And we still have our mean field equations for the flow field. Right? So that's good. And we can now question. Yes.
What's the speed of droplet? And if at that
Something
level,
like
then you just
this
replace
guy.
it by
So it's just the moment. So let's write that out exclusively. That's just gradient here. Right? That's like dramatic.
I guess it.
Yeah, you mean the alignment of
Sorry?
two ellipses. Yeah, that's fine.
That's a pneumatic tensor, 2Q averages. Yeah, I just forgot to write that out, but yeah. So that's the active stress, right? So then we know the meaning of each term here, right? That's with, no, not yet. This is self-propelled active particles that are not spherical, for example.
But it is also creating an active stress.
It's always creating a stress because they're swimming around in a fluid. You have to disturb the fluid in order to move, right? So this is activity.
Because I was thinking,
Yeah.
so people just and I was
Okay.
being something about his Travis that put that clutch and shit. That was in phase 10. Left.
Okay. Yes.
Who you fit like do a play.
Yeah.
Fluid. And like slashes out
Yeah.
that can affect the fluid.
Yeah. That's the same. Yeah.
Can affect the
Yeah. That's what we have here as well, right? So we sometimes we tend to forget that in order to move, you always have to apply force on the environment.
yeah.
That's always the case. You have to walk on the ground, which you exert a force on the ground. So does these bacteria. They exert force on the fluid. Even though the net force may be zero, but the forces are not exerted at the exact same location because they are all finite size.
Like art forms also like
Which one?
like small art.
Yeah.
You also exert force on
Yeah. You have to push against something in order to move. Always. Yeah.
but because it's a fluid, it will affect the other partition.
That's right. Because if you're working on the ground is rigid. The ground doesn't mediate interactions. But if the ground is elastic,
In terms of that,
you do as well, right?
basically, basically,
For reorientation.
to the come like this.
Yeah, so that's,
it.
you can imagine.
So you want to model the actual
effectively this
bacteria.
swims
Yeah.
and
They
you
have
reorient
to also
it,
like
right?
the expression how the
Yeah,
how the
yes, you can see
How the
that.
tail deforms as well. Yeah.
and how the fluid is again affecting the
Like correct. So you have what you have to do for the tail. And
Yeah,
the tail is
that's the same
elastic,
piece.
it's deforming,
It's the
right?
same.
So you have to do elastohydrodynamics, meaning coupling elasticity and fluid mechanics. You can do that in some extent, yes. But here we're looking at rigid particles. Yeah, that's exactly right. Yeah. Other comments? Okay, so we can let's look at these terms here. This is activity, right?
What?
So activity manifests in two places. One is they're just swimming on their own. The other is they create an active stress in the system. So this is the flow, the mean field flow. That's also from the flow. These guys we know they're diffusion. So this guy is alignment. All right.
That's because let's pretend.
So that's our model, mean field model with alignment. Any comments about this?
What's the structure? It is me.
Okay. So let's think about the exercise we did before. In the case without alignment, okay, what we did is we're trying to seek trivial solutions where it's spatially homogeneous and no flow. Let's say we still have that here. Suppose the flow is 0, okay? Zero flow, and the probability distribution is independent of x. Then Q is also independent of x, of position. So that's 0, right? We say flow is 0, so these are gone as well. So these equations look okay. The momentum and continuity looks okay. Let's check this equation. We suppose that P does not depend on space. What happens to this term? The spatial gradient. That goes to 0. We have this guy left. So let's examine that term in more detail. So consider a no flow state, meaning U is 0, and also spatially homogeneous. Which means that the probability distribution is only a function of the orientation. That's an assumption. We're trying to seek solutions of this form. Okay? We're seeking a stationary solution. Stationary means time independent. Stationary solution, but also no flow and spatially homogeneous. Make sense? Simplest we can do. Minimum. This is the bare minimum that we can try to find a solution. And then the only thing we're left with is this piece right here. Right? Because time independent, and no spatial dependence. So we're left with the third term. And what is JR here? Well, the first guy is gone because there's no flow. Yes. And we have this one minus dr. Right? So that's what we have here. So let's do this in 2D. Then we have just a single angle. I'm not going to write out this one here, but I'll leave this as is.
Can we not consider the whole thing in the book?
Which one is constant?
Diametrics of CR equals to 0.
Yeah, but I want to seek a solution that's not too trivial.
Okay.
We'll talk about that in a moment. And that's the whole point about this exercise here.
Didn't TR at the constant?
Yeah, that's what we did before. The trivial solution where it's spatially homogeneous, but also orientationally unbiased, right? So if we look at this equation here, previously, okay, we didn't have this alignment term, right? So what's the solution to that equation without this term? 0. Or a constant, not a 0, but a constant. So that's the solution we looked at before. When there's no alignment, we have a state where, so when there's no alignment, we have one state which is, randomly uniform. Then the density, right? Flow is 0. That's what we had before, correct? But with alignment, we can have a non-constant solution here because there's another term that can balance this term, gives rise to a new solution. But we can still have the no alignment term. That's still okay. So we have a new state where the system is still spatially homogeneous, but there's orientational order, which means P is not a randomly uniform distribution in orientation space. And what is that? That's just nematically aligned state, okay? Because we have incorporated alignment into our equations. So we have a new state. And let me jump onto the laptop to look at that. Okay. So these parameters, so this parameter is the volume fraction of the particles or bacteria. Forget about this one. This is a quantity that characterizes in the state. So notice that we have a few branches. So this branch here is the isotropic solution, which we had earlier before without alignment. That is spatially homogeneous, no orientational order. But here we have two new branches. Each of those have orientational order. There's a nematic alignment throughout the system. Still no flow, right? So now we have a new state. That's interesting. And the question is, are these states stable or not for our systems?
What about states?
Right. So we can do that. And here's we're not going to do that here, but here's the result. So these are still the branches. Now there are different lines because that represents whether they're stable or not. So for pushers, it's stable in this little regime here, where the volume fraction is very small. You can imagine as the volume fraction increases, this all becomes unstable actually for the pushers. And for the puller, it's slightly different. First, this branch is more stable, right, for larger volume fractions. Furthermore, there's something else that's interesting. So in this nematic branch, there's a little region that's actually stable, but everywhere else it's not. Yeah.
Yeah, we should this the bunch that we
Two what?
happening bunch of the state.
Yes. Yeah, there are two different alignment.
Okay.
Yeah. But they're all nematic. Yeah. Yeah.
Parallel branches will be
Sorry?
parallel branches actually not be.
The horizontal?
Parabolic bunch.
Yes, they are.
Those nematic.
Yeah, that's this one. The red and the green. It's the same here. It's just plotted, labeled with their stability. So they're not stable in general.
Stability over here could also not have numerical.
You do the linearization we talked about last time. When you do linearization, you get an eigenvalue problem, correct? Sometimes those can have analytical solutions, but not always. In this case, the equation you can explicitly obtain, and then it's a algebraic equation, which you can solve analytically because it's a nonlinear algebraic equation. But nonetheless, it's an algebraic equation, so you can easily find the roots. It is what you have to do, okay, to get these plots. Other comments? Okay, so we're done with mean field theory for active self-propelled particles. Those we call polar, right? They're swimming in a certain direction. And now I want to talk about nematics, which means, or specifically active nematics, which we'll talk about in the next slide. Active nematics, things like a motor protein microtubule mixtures where they do not self-propel, they only exert forces into the fluid. So before I do that, let's think about passive nematics. Passive nematics is a classical, physics subject. People talk about liquid crystal theory, and there's textbooks written for them. So it has applications. One is that of liquid crystal displays. So here's a sketch of how that works. So you have different layers. For example, this layer here does the color, and you have nematic liquid crystals sandwiched in the middle. And when you apply voltage, you can bias their orientation. So that will influence how light is transmitted through the layer. Okay, and that changes that's displayed on the screen on the monitor. So that's how a liquid crystal display works. Okay, so the question now I want to think about active pneumatics, where in addition to their behavior in the passive system, we want to add activity to it and then try to understand what happens with those systems. So pneumatics, so we're still talking about passive pneumatics. So they can have long-range orientational order like this, okay, aligned in the system. And they can develop defects, which are structural inhomogeneities or some kind of external forcing that leads to what's called a topological defect, something like this. And you can, because the director in the middle, you have a director n for each particle. It's pneumatic, which means n and minus n has no significance. It's front-back asymmetric. It's like an ellipsoid, right? So A is equal to minus. And nonetheless, you have a director that tells you which direction it is pointing at. So if you look at this green location here, there's no well-defined director at that point. You can't define it, right?
So I have a question regarding the basic question is that like I got is related to this, but
Sure.
topology, like
Topology is a math subject. Okay. You ask the math person what it means.
here topological things there.
It's math. Okay, that's all I'm gonna say about topology. So, but I can tell you more about what's the defect. It's a defect because the director, everyone else is well defined, not at the center here. How do you define the director here? You cannot. Or here.
And you know that is on the like say every particle like
You could, but that's a choice that you made. So essentially what happens is you have domains here. Okay, there are, for example, look at this one. You have 3 domains. The top domain is aligned in this direction, okay? This domain is aligned in this direction. This one is in here. So there's a conflict in the middle, right? You can't align. You're trying to align with all of them, but you cannot. So you create this defect there. And you can calculate this defect by looking at what's called the winding number. So you go around counterclockwise in a circle, winding number. Again, that's math. Okay, we're not going to talk about that, but you can, if you want, if you read the literature, you're going to find those terminologies there. So if you go around this circle and you count how much the director has rotated, and then you associate a number to that, the number is divided by, if you rotate 360, then that's 1. If you rotate in the other direction by 360, that's minus 1, and so on and so forth. But that's not the point here. The point here is, in passive pneumatic, you have these behaviors. You have long-range order. Sometimes you can have defects. What if we have activity now? An active pneumatic system, things like the motor protein microtubule solution. And it turns out activity completely destroys this long-range ordering. And perhaps that's not surprising because you're generating disturbance flow in the fluid, which will which will destroy the ordering, right?
what is the kind of activity over there? Because they might have switched from the polar.
Well, we're going to build a model in just a moment. It's just the active stress that we had before. You remember, there are 2 places where activity occurs in the mean field. One is the self-propulsion, the speed times q. The other is in the Stokes equations, where there's an additional stress term. Here,
Because of the polar acting matter, right?
no. If you exert forces, you have it.
But it why it is called activity? Like or it's
Why is doing what?
it's called activities. When it's on its own.
Because the motors are jiggling around, so they generate stresses in the fluid.
That
So it's a composite. So the motor is active, but they're attached to filaments. This composite is not moving polarly.
just because they're vibrating.
So you can think about two filament. They're doing this motion. Are they moving anywhere? They're not. They're doing this motion. They're not moving anywhere, right? But their individual components are how you exert forces in the fluid. So you still have the stress, but you don't have the polar part. So that's called pneumatic. So that active stress will destroy this non-range nematic ordering, and what happens is you get this active turbulence where you only have very short-ranged nematic alignment, and on large scales you have chaotic flow once again. Yep.
So actually, I understand the definition of pneumatics.
So nematic is in this. So let me show a sketch here. So you have a particle ellipsoid that's swimming in this direction. That's polar because when you swim in this direction, that's different from swimming in this direction, right? That's polar, meaning it has a polarity. If you have an ellipse that's not swimming, it's just doing its thing, you can still associate an orientation vector to it, but Q and minus Q does nothing to the system.
Yes.
So that's called nematic. That's all. Other comments about this? For example, if you have a passive ellipsoidal suspension, that's nematic. If you have an active that's self-propelled, that's polar. But now we're talking about active nematics, mean they are not self-propelled, but they still exert forces in the fluid. And they are still nematic, but they're active.
Oh.
And to the equations we looked at before, we'll show that in just a moment, which means you just have the active stress that's in there, but not the self-propulsion to the particles.
So can we say in some sense that the mean state that we studied
Yep.
is very low in case
Which is low?
orientation to mean?
The alignment or?
Yes.
The alignment is strong here.
Yes.
It's significant.
So the nematic word comes from essentially the long range ordering. Right?
Now it's just the geometry I looked at. That's the nematic. That's what that means. That is it. That's it. Yeah. Now long-range order is a long-range nematic order. Okay. You can have a short-range nematic order. It's locally nematic, or long-range, depending on what you have. But yeah, nematic is just this kind of dynamics that you flip the orientation, doesn't matter. Right? So, and that's our system we introduced in the first place, which is microtubules and motor protein system. So you can easily take these out in the lab, and then you can make a systems. For example, we talked about this last time, right? That lasted previously. So here you can put them in the oil-water interface, and these proteins will aggregate these microtubules, they cross-link with they form a pneumatic system. So the motor proteins are active. They are connected to the microtubules. So they can't self-propel, but they are generating forces. They're actively doing something by walking along these microtubules. So they're generating stress in fluid. Okay? So the question is, how do we model this system? And let's come back to the tablet. Turns out now we can do this fairly quickly because we've done the polar case. We just need to understand what's different now. Okay.
Just because of the
So let's write down the equation we had before.
Yes, this. I think
Let's not write the alignment for now. Just look at the original equation we had, okay, for active Brownian particles. So, well, even though these nematic particles, when you flip the sign of Q, they don't do anything to the system, but they still have a direction, right, Q, which we can use. So which means we can still write down this equation here, right, at the top. However, we don't have this term here, right? We don't have a swimming term. And that's it. That's it. So what's the consequence of that? There are a few consequences. We also talk about how to, when we want to get the number density and polar order nematic, we integrate the rotational moments of the equation. So let's try to get that. Let's look at the number density. Okay, we've done this a few times, so I'm just going to write down the equation directly. So that is it, right? Because I don't have this term Q here. I integrate over orientations, this one is gone, and then have UP becomes UN, right? The diffusive flux becomes the diffusive flux for the number density. So notice this equation doesn't depend on the polar order anymore. The reason is there's no polar order in the system. So, okay, that's good. Now, this means the following. Then we want to then look at the what's the next order we can look at? That's the nematic, right? The density, the polar order, the nematic. So we want to look at the nematic tensor. That's what we want to do. Q. After all, we're dealing with nematics, so you can see that's why this is not an important parameter. So we know this already, so we can integrate this equation to get the nematic field. All right. We're not going to do the calculation per se, but let's look at the structure here. That's the first term, right? And the second term is integrating, this QQ times the divergence of the flux, which is UP minus DT rad P dq, right? And the third term is the following. Okay, that's fine, that's good. I haven't done any calculation yet. But in these systems, diffusivity is often quite small because you have a sort of a composite structure, right? Motors linked to microtubules. So often that term is quite small in this particular context. So we don't have to leave that here. We can neglect this term, neglect the question.
Still did.
So we're specifically modeling the motor protein microtubule kind of nematic system, right? Here. And in that case, when we talk about particle, the particle is a composite particle. It's made of microtubules connected by motors. So that thing is not very diffusive. If you measure its diffusivity, it's quite small. So to leading order, we don't care about this term. It's quite weak, that's all. And then we just leave it out of the equations. And then what we have here, then we have this term here, right? And if you look at this term here, we can distribute the divergence. What's the divergence of the flow field? Any suggestions? What is the divergence of flow? That's the continuity, right? And what's the value of that? So what is this one? What is this?
If it is not zero, it is not impossible.
What is this?
Constant.
We've derived this before. That's continuity, right? So it's zero. Yes. So then gradient dot UP, you distribute the derivative. This guy is zero. Then you're left with what? U dot grad P, right? Okay, U and grad has nothing to do with orientational integral. So you just integrate QQ minus this I times P. And what do you get from that? The nematic. Okay, good. So we have U dot grad Q. Yes, good. And this thing, I don't even want to bother with doing this integration. Here, I just call that minus S. Okay, that's just doing this integration, which you can do if you want. Okay, that's fine. But we're not done yet. like we did before in the case with polar ellipsoids, where there are particle-particle interactions, such as alignment, we would still have those interactions here, because we're now looking at a very dense active nematic system.
But
Yeah, question.
the same secret.
Yeah, minus s is this interval. I've defined that as minus s. So that is minus s. Okay? So we have alignment terms, which we're just going to call that. And these notations are awfully specific because they are what people have been using, okay? So I'm just going to call that h times the number, gamma, which gamma has dimensions of diffusivity, okay? If you check the units. So these are interactions. Which we'll describe in a moment. But the point is, hopefully now you see where do you get these terms, right? So this is advection due to the flow. This is the orientational degrees of freedom when you're doing the integration. And this is the additional interactions, the nematic interactions that we're going to look at. So that is the equation for nematics. And that is it. Okay? Which means, yeah, question.
Like thermodynamics, like in Zagina equation.
Down equation. Yeah.
So how do we incorporate this? Like just vectors.
You just kill the swimming part. Everything else is still there, and you have interactions. You resolve them. That's totally fine.
Oh.
But you do have to include the active stress, the aerodynamic interactions there, because that's the only activity here, right?
Mm-hmm.
Makes sense?
Talking to say.
Exactly right. Why is that? This is not just a simple symptom. This is quite complex. So I'm gonna write down, but yeah, because as we talked about, this is a great question. We talked about before. The density is conserved. Polar order is not. Why shouldn't this be conserved?
They like me.
It can be, but not necessarily. Okay. So essentially, if you look at the structure of the equations, this is advection. This is from the integrating rotational degrees of freedom. In this context, in literature of nematics, we call that co-rotation, because you are rotating with the flow and things like that. Question?
Can we say that the whole activity does from the idea
Yeah.
in physics?
Yeah.
There's no swing.
Yeah, they don't swing.
Just identity to the
That's right.
activity.
Yeah, that's the only complete place. Okay, so here, this is the nematic relaxation. And notice the comment here that these equations at this level doesn't care about activity. And so it's just exactly copied from passive nematic theory. And hopefully that's the spirit of the whole workshop here. Much of the building pieces are from passive systems. We just need to add the active part to these equations. Of course, we'll have to understand how we add them, but that's it. And this one is complex, okay? This one is borrowed from liquid crystal theory. That's a free energy of molecular field align. There are a few terms here.
But why? How when we got splitting mass chain and gene is already getting it?
This still gives you a force. You can only talk about this individual term. You can't say the whole system. You're adding a new term to these equations, right? This model, for example, this is elastic energy, right? That's elasticity. That's still there. That's totally fine. You can't form a free energy for the whole system, but if you're looking at what kind of forces you're getting,
Field, right?
sorry,
It's a whole field that the king Q squared Q by 4.
that's a model that you've taken. So there are a few. Forget about the details here, but physically, let's think about it. This term we should already be able to understand. The first term here, what does that mean? Q squared. Any guesses? So we have these many terms here, right? So the way to write this down, of course, has nothing to do with active matter. This is classical crystal theory. The way to write down these terms is to look at what terms are permitted by symmetry. There are certain symmetries that we have to respect. And these are lowest order Those were terms that you hold. You can add more, but that's not the point. And this one is elasticity. And you're adding.
Electron field.
It is, yes. That's correct.
Good.
And this derivative here that looks quite complex, that's just due to the nematic tensor is funny, okay? You see there are traces here because Q is trace free and you get that term, that's from math, okay? But the point is you have these interaction terms that you have and there's no activity here. And where is that? That is here. We have previously had the mean field velocity equation, right? The Stokes equations with the active stress. So now I've just rewritten them into different components. So we have the viscous stress, which is the pressure plus the viscosity term. The active stress, which we had before, that's the magnitude times the nematic. Because we have elastic interactions in the active nematics, we have an elastic stress tensor. That's all. So the only new term is this one compared to passive nematics. That's it. And hopefully now you see where these equations come from. If you now go into the literature, you read the papers, you know how they are derived.
There are different forms of this sampling stress, or this is the only form?
This is you can have other forms depending on the context, but for now you see that this is only, we're looking at force dipoles, right? That's how this came about.
Almost the same flight we have done for the cell.
It's not almost the same. It's exactly the same stress.
Yes, because over there it is USQ and over there sigma Q4. We can
No, that's also sigma. It's not, USQ is self-propulsion, but the stress term is still the same. Here, I mean, this average is Q, sigma naught times Q. It's not different, it's not almost, it's exactly the same. Okay? So, guess we're here, right? So that's active pneumatics. But we don't want to deal with that complicated equation there. So let's simplify it a little bit. We're looking at these motor condensing microtubule mixtures. So the active energy, the time scale that this activity are happening are much faster than elastic relaxation. So let's just remove those things. And we should only keep this final term here. So let's remove these guys to do a simplest model. So we've set ABC to be 0. Okay, that's all we've done. Like, then you have this equation. And I've removed the elastic stress because that is slow, okay, compared to active. So this is the simplest hydrodynamic theory that you have, and this is often used in the literature. And now you see where these equations come from. So again, this is a repeating theme of things today is in the absence of boundaries, these long question.
So, you were saying where hydrodynamics methodology does that mean?
It's mediated by hydrodynamics. It's not doing the role. It's because of the forces the swimmers are exerting on the fluid, and then that's transmitted, felt by other particles.
So it depends.
Yeah.
So suppose if I add up, like if bacteria is a passive, would that really add a lot?
Oh, okay. So you're thinking about a complex system where you have a swimmer moving in pneumatic. Yes.
So suppose bacteria is moving in a passive material, and if another case bacteria is moving in a active direction. So how about this thing gives a really very strong service?
How what is different?
How is it actually measure the activity that is 0 to such a first? I just want to visualize how the activity in the negative spectrum because I'm using the different breaking passive dynamics and active
Passive pneumatics, you don't have this term.
Yeah, but this helps us
This term is coupled. This term is proportional to Q.
out.
So it's coupled to the pneumatic evolution. Whereas for passive, we don't have this at all.
So let's say that there is a scenario like there are like tests that is minimized,
Yes,
and there is a passive pneumatic.
Passive pneumatic is not only it's a bad ellipsoid. This is a moving. It's a sliding ellipsoid. It's a composite.
Stress created in the
That's
machine.
exactly
And
correct.
that is the active stress.
Yes. Yeah.
And if you place a bacteria inside it, which also still propels.
You're making a complex system. You have a passive pneumatic and you put a bacteria in there. Yeah, you can do that. But the passive pneumatic is still passive pneumatic, but then the single active streamer is gonna disturb the medium. So that's fine. There is an active pneumatic. Okay.
So it means
Yes, there is already an active pneumatic.
Yeah.
And if we have some passive particles inside it,
Sure.
so it will go, right? Because of the active pneumatic.
You can go. You'll be kicked around. Yeah.
We kicked it out.
Yeah.
But now there is, instead of an like passive particle,
Yeah.
in the active pneumatic medium, we are
Okay.
putting an active rubber particle. So this is.
Okay.
So then there will be two kind of active.
Yeah. That's right. And then you have to analyze that more carefully, because it's a complex system, though. And yeah, you can do that. That's fine.
sure. Because we get a model protein which are included in our body. Is it has some unique involved that is contained here. So like the crossword cytoscape
Yeah.
that they are restricted. So somehow you should modeling this to like that. Like if you consider this protein as a like active.
Yeah, that's this one. And this model is that cytoskeleton structure for us. Yeah. That's right. Yeah.
Okay.
Okay, that's great. So I guess the main thing that I want you guys to appreciate is polar, acting polar, or the mean field theory developed for the polar system. And for this one, if you just look at the final equations, they look nothing like each other, but they're quite similar, okay, in terms of how you derive them. So that's the message that I'm trying to get at, okay? Other comments?
I was saying that's it's a historical thing I want to go. Saying are these two things like found out in the same amount of portion of same type or?
Yeah, we know this. People know this. People know they're the same. It's just if you're just coming into the field.
Saying, like in the US was realized.
They're developed at the same time, and we know all about we know this everything that I talked about. This is not new. Nothing's new here. And if you think about pneumatic liquid calcium liquid crystals, people have been doing that for decades. There are tons of textbooks written on them. And on the other side, the Chomsky equation, we know that as well. We know all of this. It's just as a person who just entered the field, if you look at papers, you would feel like, oh, there are so many different things that's going on. There are hundreds of papers out every day. It's a very hot subject now. So there's a barrier of trying to identify what's actually happening, okay? But they're not from completely different origins. They're the same origin. I mean, you're just doing statistical mechanics of particles. How different can they be, right?
The question is there. Suppose we are the same here. This is the right region. We are the same one. My daughter is already now here. So what kind of data is allowed?
What kind of
So result is like
simulation? Are you talking about Langevin kind of simulation or mean field?
like I want to know the techniques. I know all my character.
So if you do the mean field level, you're just solving PDEs, then there's nothing special. You just solve PDEs using whatever PDE solver you like to use. If you're doing the Langevin,
Yeah, but that body together was
then you're talking about Langevin equations, right? You're doing microstructure. You're simulating the individual particles. Then it's the same as before. We talked about you have write down your equations of motion for individual particles and represent their interactions. Then you evolve them over time. And then if you want to get at the mean field quantities, you do average. Because if you're doing the microscopic simulation, you have all the information you want. You just average them to get these things. Yeah.
but
It's computationally costly, but conceptually no different from what we're doing. So that's another theme of these things. Conceptually, it's fine. Computationally, it's complex, but that's not part of physics. Yeah.
need to reduce this calculation of cost.
You can't. Of course, there are optimizations you can do, which we talk about, for example, the cell list, neighbor list. But those are only just to remove computations that are, in the first place, unnecessary. Because, for example, I have a particle here far away. If I do it naively, I'm trying to resolve our interaction. But I know we have no interaction. So these optimizations you do mathematically are only to remove unnecessary computations. you can't remove necessary computations because you can't get something out of nothing, philosophically. So no, it's computationally heavy, and that's why in simulations, we use high performance GPUs to do them because we need more computational power. Okay, yeah. Other comments, questions. So in the absence of boundaries, as we talked about before, in a different context, so in this case, the nematic state is unstable. You again can do a linear stability analysis to figure that out. And this is unstable to any level of activity. So long as it's finite, it becomes unstable. And here's an experimental snapshot of the system. Again, you see this defect that develops, then you can do simulations with the PDs we talk about. You can more or less recapitulate what happens in an experiment. And that concludes our lecture in the morning. So we started early, so we'll get to end early, and we'll come back in the afternoon, which are tutorials, where I won't be teaching you things. I will be sitting here trying to answer your questions about simulation. And
Yeah. Or simulation based. So, say we look at the body self-propelling things with active patterns.
you can model self-propelled things with active.
Like say this is the question I heard before, so I'm just going to ask the information. So you say in a very amorphous medium, there is some kind of defect,
Okay.
which was
Defect dynamics. Okay.
so that effect that moves around. Can you model that in an active pattern?
You can. People have done that. Yeah. You can. They're active. And in the case of the pneumatic, the active pneumatics, the defects move around because they are active. Yeah. Yeah, you can do that. But of course, then you have to figure out their velocity, and you can do those by measurements, things like that. Yeah. Great. All right. Thanks, everyone. We'll meet again. Is it at 2:30 or? Okay, 2:30.